So welcome everybody to the journal's 5th webinar. This time the topic is energy storage. And we've encountered vivid and unprecedented interest for these topics thanks to the current geopolitical situation and crisis. So basically Europe is rushing to accelerate its renewables build out, not only to exit fossil fuel-based power, but also to wean itself off Russian gas imports. But it needs energy storage to turn fluctuating wind and solar power into stable baseload energy supply. The largest markets at the moment is Asia Pacific as well as North America, and Europe is still playing some catch up. And I'm pleased to be joined by a panel of expert speakers who will tell us more about the various technologies out there as well as the project economics. I'd like to introduce and welcome Dr. Thorsten Kroll from Siemens Energy. He's a key expert on the integration of renewables into reliable and stable large, as well as smaller decentralized grid environments. He develops hybrid solutions fit for purpose, holds a PhD in physics, and has been with Siemens for 16 years. Holger is joined by his colleague, Thorsten is joined by his colleague Holger Wolfschmidt, who is a key expert in electrochemical energy storage systems and their market applications. Holger holds 100 patents through his PhD in physical chemistry and is looking into R&D and business development for battery energy storage. Holger, I think you need to unmute your microphone, please. We are also joined from over in the US, by Joseph Ferrari, Regional Sales Manager for the United States and Canada at MAN Energy Solutions. Joseph has close to 2 decades experience in the energy space and has a key eye on helping customers meet their clean energy targets. He's developing go-to-market strategies on new solutions, especially molten salt energy storage. Also from over in the US, we are joined by Luc Wittmer, General Manager Data Science at Wärtsilä Energy Storage and Optimization. Luc is managing the research and development of automated hybrid power plant dispatch for island grids, and also auto bidding system for merchant electricity markets, and he leads Wärtsilä's power system simulation efforts. So let's get us all started by asking you, Thorsten, to tell us more about the reason behind the current rapid growth in energy storage systems. What is driving demand? Is it the need for standalone storage for grid balancing? Or is it rather the need to integrate storage into hybrid power plants? Thorsten, the floor is yours.
I would say thank you for the question and thanks for the introduction, Anja. I would say a little bit of both, because the storage world currently, so coming from the old reliable power supply systems, where, let me say, majority of the generation has been taken in the past by flexible thermal power generation. In the new world, of course, intimacy coming from the renewables need to be balanced out somehow. And the key point is, as soon as we reach excess renewable power, this power should be used in the future as green as possible, and we need to store it to have, for example, during dark doldrums power available, but also on the balancing side, on the very quick side, and so on. So we need to use, to decarbonize the world, we need to use excess power, and of course this must be stored. And there are several options out, of course. We can do it on the mechanical way, thermal, electric, storing electricity directly in batteries, and so on and so on. So there's a huge variety of different storage technologies out.
Sure. Joseph, could you help us out? What, in your view, is the reason for today's rapid growth in energy storage demand?
Well, the reason, I think, has to do, obviously, with decarbonization. I mean, we need wind, solar, hydro, nuclear, carbon-free resources, but most of those are not 100% reliable. And to fill in the gaps at multiple timescales, we need different storage technologies. So, for example, things like flywheels or lithium-ion batteries are great for balancing wind and solar in real time, but most power systems are not. Oh. Go ahead.
No, continue. So what? Continue, please.
Oh, I was just going to say that most power systems, like in the U.S., Texas, and California, are approaching 30+% renewable penetration, and they're only now starting to see the challenges. I mean, they've seen them, but they're realizing that they need more flexible things like battery storage to balance the system. But as they get to higher renewable penetrations, they're going to need longer duration energy storage systems to bridge gaps that might last more than 8 to 12 hours or so, and also have to deal with what Torsten had mentioned is, seasonal variation, disruptions in weather that might require days to weeks of storage. So we're not quite there, because right now in many systems, they can just use fossil fuels to fill in those gaps. But as we get to higher renewable penetrations and closer to those 100% targets, we're going to need much different timescales of storage, going beyond minutes to hours into hours to days and to weeks.
Yeah, sure. Luke, can you add to this, please?
Yeah, I mean, it's definitely a both and situation, as both Torsten and Joe said. There's a lot of different technologies that are gaining traction, riding down their various cost curves, becoming cost competitive as the rest of the energy landscape evolves. Lithium-ion batteries today are still one of the main players for a couple reasons, and growing because they're very cost effective. Durations are also increasing. A few years ago, let's see here, like back in 2014, 15, all the batteries, lithium-ion batteries that were being deployed were 15 and 20-minute systems, very high power, short duration. 3 years ago, 2019, 2020 timeframe, the average system size that Wärtsilä was delivering was around 1 hour. Today, it's much closer to 2 hours, and there's places like California that mandate 4-hour systems, and lithium-ion is fitting into that context. Even with those, a 4-hour system is more expensive than a 1-hour system, but compared to the alternatives, the commercial scaling challenges and availability of things like power to X are still very young and getting there. And so lithium-ion batteries are filling that gap today.
All right, sure. Interesting. Holger, let's look at growth and try to quantify growth. I understand that Bloomberg New Energy Finance is saying that the rapid renewable build out requires energy storage of up to 360 gigawatt capacity by the end of 2030, which would be more than 20 times the capacity we have installed today. Do you agree with this growth forecast?
Thanks for this excellent question. To discuss about growth in the energy field is each and every year a fantastic discussion, because all the analyst reports normally from the years above, you have to correct to higher numbers. So I totally agree, and I think it's a great forecast. It's just depending if it's a yearly growth rate of 10, 20, or 30%. And I think let's give me the time to give the curse to the photovoltaic. What's happened 20 years ago? A tremendous increase in installations, a tremendous decrease in price, and a tremendous increase in quality. And this is what we do have also in the field of storage. So mainly batteries, of course, at the moment, but this is let's say the tremendous basis of this growth. And I also really like to mention that storage or flexibility is, in my opinion, a kind of a Swiss knife of the electricity system. It's precise, it's really precise and sharp, it's multifunctional, and looking at a Swiss knife, you have always the right tool in hand to solve the problems. So, and this is, I think, the great success story of storage, and also the great projections in future.
So comparing storage to renewables, Holger, would you say the growth of storage is equally rapid as the growth of wind and solar, or is that due to Europe's need to wean itself off gas? Will it be even more rapid? I mean, we are living in a special situation at the moment.
I think it's strongly coupled. it's really strongly covered. I cannot state if it's a factor 2 or 3 or 2.5, but there's a strong coupled of increase of renewables and increase of storage or flexibility. And we are talking about all kinds of flexibilities, because I doubt there's only one way out.
Okay, yeah, all right. So let's go right into the technology. So Luke, I'd like you to tell us about what types of storage technologies out there and at what stage of maturity. Please specify the energy density, the rechargeability, load management potential, and especially also costs of these various storage technology types.
Yeah, so Joe mentioned a few of them briefly in the beginning, right? So you have sort of some more traditional ones like pumped hydro, move water uphill and let it flow back downhill, gravity-based storage. There's a few other companies trying some things in that space in the gravity storage. So you take potential energy. There's chemical energy, so converting taking extra renewables, converting it to a methane equivalent, and storing that in tanks as a chemical that then you can store indefinitely, and then you would burn it as a carbon neutral fuel because it was generated from a zero carbon source later in a traditional thermal power plant. You've got battery systems, so electrochemical storage. There's a bunch of them. There's your lead acid batteries in your car, but those have not really shown any capability to scale. You've got lithium ion batteries. There's a few different types. You've got different types of lithium ion chemistries. NMC was a very big one a few years ago, but LFP has really ramped up a lot. So NMC is nickel, manganese, cobalt, and LFP is lithium iron phosphate. So these batteries have a little bit different densities. So you asked specifically about that. The LFP is a little less energy dense, but it's also a little bit more stable. And that's one of the reasons people have moved to it. And it's simply cheaper. It's a very good technology, and that's why it's really been picking up speed the last couple of years as manufacturing has ramped up for that battery. And anybody who's doing energy storage integration sort of has been on that path and was heavily invested in NMC, and now today is heavily invested in LFP. That's not just a Wärtsilä thing. That's everybody. Right now, there's all of the global supply chain issues. So from the pandemic through to the current, crisis, with Ukraine, there's just a lot of global challenges that we are facing in terms of supply chain, and so the costs of these batteries have continued to decline. But this year we're seeing, a little bit of a difference there that I can't go into too much detail, but we're impacted in the same way the rest of the world is on some of these supply chain issues. And I think that's just something that's worth mentioning here. And it's a small bump in the road. The technology continues to decline down the cost curve the same way that solar did. And batteries are very efficient. You asked about rechargeability. That's one of the main reasons lithium ion batteries have gotten such traction today, is that they don't have significant hysteresis issues like lead acid batteries can have. You can do a whole bunch of little microcycles, and as long as you have the right software controls and a good BMS that's estimating the state of charge and all this stuff, you can have a very reliable technology that it's very dispatchable. And I really appreciated Holger's comment about a Swiss Army knife. It's an analogy that has been used and is very well suited to lithium ion batteries. They fit all kinds of applications and they solve a lot of different electrical problems in any context you put them in.
Great, thanks a lot for this overview, Luke. Torsten, would you like to add to that? I'd be interested in the cost side of things. So have costs gone up for certain battery storage types due to supply chain issues? Could you add to this, please?
I can add to that, but I would extend a little bit also the storage technologies, because also the storage technologies, of course, highly depend on the time scale which is required, response times, and also the capacities. And this is a very big topic, of course, for solving the topics on the grid side, but also for specific customers. So adding to the pumped hydro and battery systems, we also could add something like a thermal storage topics, all for very, very fast response times, short storage durations, flywheels or supercapacitors, which are used for grid stability purposes. Especially based on the flywheel storage, of course, the dynamic to keep a grid stable with a high share of renewables. Rotating mass inertia is really a very important point to be able to keep it in operation, to keep the grid stable and to keep the system running. Coming to your question right now with respect to the prices, of course, if you have a look currently on the raw materials, especially right now in the newest political developments, in these cases, material prices have been exploding. The impact on the systems is
Yeah, I can
not yet, but it will come up. Just to give you directly out of my head one of the numbers. For example, the price per ton of nickel, which is also used in some battery systems and many also magnetic systems and so on. The nickel price have been increasing within the last 5 weeks, coming from 15,000 euro per ton nickel right now of more than 50,000.
Wow.
In the time right now, these increases of prices have not been priced in, but this will come. So it is expected that really the prices will boost up a bit in these cases. On the other side, also, there's a very, very good study out from IEA, which shows which kind of materials are be used in the future to drive all of the decarbonization every countries have committed to. And this will show, for example, for lithium, compared to the production of 2019, 2020, by 2040, the production and the demand will increase by a factor of more than 40, which of course will have another effect also on the prices. So there are two effects. The one is the prices of raw material are expected to increase. On the other side, of course, due to scale up effects, the prices might get down, costs might get down. We need to see really what the impact will be in the upcoming months. Unfortunately, I cannot give you a closed answer. It will reduce 10% per year.
All right. Thanks for explaining this. Sure. Holger, customers need to quickly store excess renewable energy. So I understand electrochemical batteries, they need both fast charge capability, but also long cycle lives of beyond 1,000 cycles. Could you explain to us which battery type has these qualities?
Sure. Very short and precise answer. Lithium is here the main worker in this space.
Oh.
So fast charging is not an issue at all. It depends on the power electronics and the controls. So this is the main precondition that everything works fine in both directions, charging and discharging. So number one, not an issue at all. And a little bit elaborate on cycle number. This is a mystery, and a glass ball. But compared to mobile phones and laptops, the industry-grade batteries in the stationary applications are complete different stories. So you can easily operate 5,000 or 8,000 cycles, or maybe even 10,000 cycles, a little bit depending on the application, of course. But this is not really the big issue. And the most important stuff, talking to all world outside, is not compare it with your mobile phone or laptop or toothbrush. Yeah, it's a complete different story.
All right, sure.
Be relaxed, sit on your sofa, and you can operate your system 10, 15, or 20 years.
Okay. Luc, would you want to add to this?
No, Holger said it perfectly.
All right. So let's go on. Some critics say that lithium-ion batteries might have already hit their performance ceiling. Is this true? And if not, how could they be further enhanced? Let's ask Holger again.
So there's always room for improvement from a technology point of view. There is chance on making the materials better. Of course, there is chance to increase a little bit the voltage. There is chance to increase the efficiency. I think this is really step-by-step approach. But on the other side, it's a chemical element given with some boundary conditions, and you cannot just cross given laws from chemistry and physics. Yeah, this is not possible. You're reaching, of course, step by step the ceiling, but there is room for improvement if we go to solid state or less cobalt content and higher energy density. But I would say this is an incremental improvement over the time, over the month, or over the years. As I said, room for improvement, but no quantum change. Yeah, so will not easily fly to the Mars or the Moon. Also.
Sure. Okay. Let's look at molten salt energy storage. Joseph, please tell us what are the unique characteristics of this storage type and where can they be best put to use?
Yeah, so molten salt is a form of, or being considered as a form of long duration energy storage. And it's compared in the same arena as, say, pumped hydro or compressed air, liquid air, gravity type systems. But the one unique feature of molten salt is that it stores renewable electricity or renewable energy as heat in a tank. And then it can use that heat to generate steam, which then turns a steam turbine. What's unique about this is that the salt can be heated by any number of means. It can be heated directly by solar, like in a concentrated solar power plant. It can be heated by renewable electricity using electric heaters or heat pumps. But it can also be heated by the combustion of renewable fuel. And what this does is it allows a molten salt power system or energy storage system to do its thing day to day, taking renewable energy, say solar during the day, then releasing it at night. But if you have a cloudy day or a series of cloudy days, and there's not enough solar to meet load, let alone charge long duration energy storage systems, you have the option of having a backup fuel burner that can burn something like hydrogen or ammonia, e-methanol, synthetic methane, carbon neutral, carbon free type of fuels. The one advantage that this brings is a little bit conceptual, but it's important. It allows molten salt to be considered as firm capacity with a capacity rating of 1.0 under all conditions, with the fuel burner as backup. And this is in comparison to solar, wind, batteries, many other types of energy storage systems, which are not given a capacity rating of 1.0 under all conditions. So when utilities have to meet a capacity reserve margin for reliability purposes, they can get a real big bang for their dollar with these molten salt systems, because every megawatt installed counts as a megawatt towards capacity. So that's one unique for power to power applications. The other unique feature of it is the molten salt. I would say that 2 out of 3 inquiries I get for molten salt applications are not power to power. They are industrial processes, oil to gas, chemical manufacturing facilities, wood and pulp, paper processing facilities that have a high steam demand. And molten salt, I said you store the heat in the molten salt to produce steam, but it does not have to go to a steam turbine. It can directly produce steam and decarbonize multiple industries that are difficult to decarbonize.
All right, very interesting. Let's look at thermal storage. Torsten, could you tell us what role thermal storage is playing in the future and where are the sweet spots of this technology type?
Yeah, I think the thermal storage, molten salt is one of the thermal storage technologies. Thermal storage is a very interesting point because not only the power sector needs to be decarbonized, as just discussed, of course, the industrial needs to be decarbonized, but also topics like district heating on a lower temperature level become a bigger and bigger topic also across Europe. It of course high depends on the temperature levels, which kind of thermal storage technologies are to be used. Of course, on the very low temperature side, for district heating or something like that, a huge hot water tank is the best and cheapest way for the thermal storage arena. Molten's one of the very good or the best technologies, of course, if you want to store based on heat like concentrated solar power. For example, in the north of Africa, we have built about 10 years ago an integrated plant where we have 180,000 square meters of concentrated solar power based on molten salt. And this is combined with a combined cycle gas turbine power plant. So the heat is stored, created, and the efficiency is raised. And of course, the CO2 emissions are reduced just based on these hybrid solutions. And thinking heat, of course, is also in the future thinking hybrid. Heat and hybrid is always very well connected. And just due to the fact that also the industries have to decarbonize, the heat integration and power generation, local systems, decentralized systems in the future become more and more important also to decarbonize the industry. And then it's just a question of the temperature level, the capacity, and the medium you want to use. You can use lava stones, you can use molten salt in the low temperature arena, hot pressurized water, or whatever.
Actually, Thorsten, your question brings us right to the economic side of things. Let me jump to the questions on industries having spent a lot of money on on-site power generation. And these fossil-based power plants, they're now trying to decarbonize. Are they using energy storage combined with renewables to turn these fossil plants into hybrids? And if so, which industries are spending the most? Which are the front runners who are trying to green up their on-site plants?
Question again to me?
Yeah, to you. Yeah.
Okay.
You are our hybrid expert here.
Yeah, currently there are many industries. So some really try to do it to reduce the energy bill. Front run with a very green commitments done toward the society are, for example, data centers. They committed in many cases for very green solutions, but compared with very high availability guarantees. They currently really try to decarbonize worldwide. But there are other industries, many other industries like mining industry, also which have in the future off-grid solutions. They want to decarbonize as well. They are going into the direction to install renewables on site or close to site. And all of them have very high requirements on availability, but also on the combination, power and heat. For example, we have just been discussing a project in cold ambient conditions. During winter time, the temperatures go in this mining complex down to -50°C outside temperature. But they are underground. They have to use the combined cycle power plant and the CHP power plant just to heat up the air pushed underground. Because with -50°C, freeze the whole mine.
Oh,
so these kind of industries are very
interesting. Joseph, I see you nodding. I'm sure you can add to this. I'm sure you have projects there.
I agree 100%. I agree 100%. Mines, it depends on the country and the application, but if you look at Canada, for example, they recently passed some laws with, steep CO2 taxes. So mining concerns are strongly looking at, an all of the above approach. And it's not going to be all solar or all wind or, just batteries. It's going to be the combination of wind, solar, batteries, renewable fuels, thermal assets, everything, because they need to, mines in particular they need 100% reliability. They can't be subject to the vagaries of wind and solar. They can't worry about whether a storm is going to block solar for a week or not. They need to be online all the time. One other thing, and Torsten, that was a great summary. One thing that I also see is that in the US in particular, institutions like universities, hospital complexes, some municipalities, they want to decarbonize as well, and they have very strong commitments to do so. And they're going through, I would say, a renaissance of hot water or steam to hot water conversion. So they have boiler systems running on fossil fuels now, producing steam for the complex. And also they have additional chillers, for example, to provide cold. With newer, say, heat pump-based electrothermal energy storage systems, we can produce hot water, very hot water, 150 plus degrees Celsius, which allows these systems to use their steam pipes as is. So it allows for a one-to-one drop-in replacement. They can also generate ice and cold simultaneously. So there are a number of, and a growing number of applications of these types of complexes looking towards heat pump solutions, not for molten salt energy storage, but for hot water storage. So they want to be able to rely on, energy arbitrage when there's overproduction of renewables, very low energy price. They want to absorb as much of that energy as possible and bank up either hot water and or ice, so that when the prices go up at some other time of the day, they can just rely on the stored heat or stored energy, hot and cold, to meet their load. And in this way, they can achieve significant decarbonization results in a pretty easy fashion.
Right.
Anja, I would like to add just a minute, because there are also other industries not only interested in decarbonizing their power. There are also a couple of industries affected with the increasing instabilities coming from the grid, and they will need also hybrid solutions to keep the system stable, to, let me say, as something like a risk prevention, that if something happens on the grid, if flickers come in, that equipment goes into protection, so the stability points becomes more and more a key factor also for the industrial solutions as well. So this needs to be kept into consideration when we talk about storage solutions.
Yeah.
Many utilities are offering that. There are certain industrials that might be at the end of a line or something where, the cost of a transmission upgrade would be prohibitive, but they can put a battery or something behind the meter to absorb those fluctuations in real time. And it's a more cost-effective solution for everybody involved.
Yes.
Okay. Looking at grid stability, I'd like to specifically compare the economics of storing the surplus wind and solar energy in batteries, let's say batteries, with building a fast ramp gas-fired peaking plant. So in which market is energy storage actually more economic than gas peakers? Torsten or Holger, would you like to answer this?
I can jump in.
Please.
But I cannot give you a super precise answer on this. Yeah, so I can try to summarize, but a precise answer is super hard. And I think it's a little bit dependent on what storage is. Yeah, you have a flexibility tool with a given duration, which can cover a given flexibility.
Yeah.
So you have, let's say, an asset for 2 or 4 or 6 or 8 hours. Someone in the chat asked also about redox flow batteries. Also, of course, these can be a part of the overall system. So you can, let's say, homogenize your output of a photovoltaic park, great, yeah. With a battery, even enhanced output, you can smoothen it, great, really great. A little bit different, and we talked about this with the utilities. It's a question of security of supply. And make energy cheap is super. Yeah, I'm happy if my invoice will decrease, but also looking really about security of supply. And this means mix at the end. So unfortunately, Anja, no precise answer to the question where it's best suited. It depends on.
Right, Luke, maybe you can give me some idea. I just wanted to know, is it more attractive to invest into energy storage to stabilize the grid or into gas-fired peaking plants? Let's say in the US market.
I think the conversation is very clear. There's not a one size fits all. And I think one of the factors that impacts people's decisions on this is availability and supply of gas. So I think that's sort of a very important underlying thing here. In I think it was 16, maybe it was 17, there was a gas supply leak in Southern California, and that was a big boost to some of the first big grid scale batteries in California, because they couldn't get the gas lines fixed, and there was a need to have this peaking capacity there. So it was like, well, if we can't get gas, battery is the next. It's a little more expensive than gas in this application, but there isn't a choice, so we're doing it. And if you look at, one of the questions you asked was, you could buy a new fast ramping plant, but you also have all of these existing pretty efficient combined cycle gas plants all around your grid. The challenge is that those combined cycle plants take an hour and a half to ramp up to full load, and so you can have fast ramping start conditions, but they're more expensive. They cause more wear and tear. If you start it nice and steady, then you're not causing a bunch of maintenance events. And so that also sort of says, well, if it's going to take so long to start these plants, I should have some battery to stand in the gap, because wind and solar can ramp out in a matter of 15 minutes for large plants. Even across a big area, they could quickly ramp out in different weather conditions. And then finally, on this underlying concept of gas availability, in the hybridization of the mining sector that was mentioned a bunch, most of these plants are running on heavy fuel oil or diesel. They don't have access to a gas supply line. It's not the same situation Europe's in with Russia and the gas lines there. It's that these mines are just remote. They're in the middle of nowhere. And so you have to have fuel convoys or other ways to get fuel there. And so it's not a gas versus battery question. It's a very expensive, high carbon intensity fuel versus batteries. And that choice today is a no-brainer.
All right, yeah, sure. Good. Holger, I have another question for you. Please.
Anya, could I just
please
pile
go
in real
ahead.
quick to what Luke was saying? I think Luke is 100% right. It's not really a comparison of a gas peaker versus a battery per se. But as we look into the future, if we step outside of right now today, if you look at planning exercises that different utilities or grid operators do, looking at, say, the trajectory or the path to 100%, there is definitely a place for gas peaking plants all throughout the horizon, even at the 100% end state. Gas peakers have like recips or some gas turbines, they have some advantages in that they're relatively cheap. I mean, $500 to $800 a kilowatt EPC price. And there are fairly well-defined sort of exit ramps defined by the manufacturers on how to transition these units from today's fossil gas to tomorrow's renewable fuel. It could be hydrogen, it could be e-methanol, it could be synthetic methane, it could be one of those. So you see a lot of utilities today who are 100% committed to decarbonization. They're installing a ton of wind, a ton of solar, they're installing a ton of batteries, but they're not giving up on peakers. They're keeping them in the system because I like to call them the reliability backstop mechanism. They're there and they can run for weeks to months if need be. And ultimately, when we transition to renewable fuels, whether it's a cryogenic ammonia tank, a gas storage facility with carbon neutral synthetic methane, or just a dumb ammonia tank full of liquid sitting there to power these devices, all of those fuels are a very dense form of renewable energy storage. So they're not the cheapest form of energy storage, but when you look at the dispatch, least cost dispatch, they're going to take wind, solar, hydro right up front. They're going to use batteries to fill in the gaps in real time for short durations, 4 or 6 hours perhaps. They're going to use things like pumped hydro, compressed air, liquid air for 8 to 12 or more hour. But then when they have a week-long storm that's compromising wind or solar, or a seasonal lull in either of those, they're going to need something else to fill in the gaps. And that's where I think the peakers still have a relevant place.
Yeah. And
okay, so it's a both and not a one versus the other.
Yes, there's plenty of room for all of us to play.
And Anja,
Right.
before you just continue, just give me 30 additional seconds on this. Because one of the topics is at some point in time, if you have very fast fluctuating things where maybe batteries need to step in frequently, if you do not have sufficient time to charge the batteries in between, then of course they fall apart. So this will be as a backup security supply and so on, it will always stay, the rotating equipment or the thermal equipment will stay an aim as beaker also for these purposes. And we have seen some countries already who build up the system completely new, especially in the fast dynamic and the primary, secondary control systems, the tertiary control system, like for example in Ireland, starting with the dynamic things, adding flywheels, then going on battery storage. Right now, I think something like ready for 2 to 3 hours, which could be used based on storage, but the thermal thing is always available as a backup from the backup.
If I can just add one example, one of my favorite examples.
On the batteries, I actually have a questions from our audience. Yeah, Joe, and then I come with a question from the audience. Joe, please go ahead.
Oh, just real quick, one of my favorite examples is HECO, the utility on Hawaii. As far back, this is ancient times, back in 2016, 2017, right? They're very progressive, very serious about 100% decarbonization. And one thing that they did in planning out their system is they looked at weather data going back as far as they had collected data. And one thing they found is that maybe once in every 10 years, they can have up to 6 weeks of continuous rain. So you can imagine what this does to solar. It compromises wind. They realized they can't put enough batteries on the island to power the place for 6 weeks continuously. But then they thought, you know what, we have a bunch of oil-fired plants on the island. It doesn't have to be fossil oil. They can basically fill those tanks with some form of, say, biodiesel or renewable diesel and keep those plants there as a reliability asset to basically have something in the background as a backstop that might only be needed once every couple of years, but when it's needed, it's really needed. And the most important thing is they've already paid for this. It's in the ground. They don't have to do anything different. So I'm seeing that with a lot of utilities as they plan out for their future, that there's going to be some form of renewable fuel augmenting their system.
Okay. I'd like to ask a question from the audience. One person is asking, the manufacturers give 10 years warranty on batteries. How can we test if these batteries are actually still working in 10 years' time? He's assuming not all the manufacturers will be around in 10 years' time. So is there an easy way to quickly check the battery life and quality or a device? Any takers for this?
Yeah, sure.
Luke, please.
Yeah, so you'd run a simple capacity test, right? And so it would have some degrading curve of capacity, some guaranteed amount of energy capacity at year 10. So if it was originally a 100 megawatt hour battery, maybe in year 10, it's only a 70 megawatt hour battery. And so you'd run the test, you'd fully charge it, fully discharge it, measure everything and say, okay, it either achieved this 70 megawatt hours or it didn't. And to the point of, companies being around, well, you'd better pick a company that's been around for over 100 years. There's only a few of us here, pick one of us. And we plan to still be around in 10 years and we have a pretty good bankroll. So, our warranty's good. You've got to trust us. We have labs, we have researchers, we have very close integrations with our supply chain partners in China and Korea and around the world. And you have to sort of make sure that there's that financial backing behind a warranty, but if it's there, you should trust it.
Sure. Holger, would you like to add to this one?
Especially in this question, I can sleep very well with projections in future about sensor and monitoring battery systems. So it's really a close sensing modules on top. We have excellent battery management systems. So yes, it's a newer technology, but I have no doubt you will find normally some strange stuff. If something is ongoing in the battery system, you can monitor it precisely. And so no real issue to extend after 10 or 15 years lifetime operation. So it's just given, and it's not a system you put in the middle of nowhere, go to church and pray and hope everything will go fine. Yeah, not at all. Yeah, it's closely monitored. And normally with close integration, what Luc mentioned with Asian suppliers at the moment. So I have no doubt for this long operation.
Good. Another listener to our webinar is asking about the material constraints and the logistic struggles given the current geopolitical crisis and the ongoing war, basically. How do these parameters impact the speed and cost of the energy transition? And is there a way out, basically? Torsten, would you like to talk about this one? He wants to know about how these material constraints are impacting on cost, on battery cost.
They will, from my personal point of view, I cannot make a complete statement because we are not producing cells and so on, but from my personal point of view, they will impact the prices, but also currently the mining companies and the materials companies are currently heavily working on different processes. So in the past, of course, the way is digging high-grade ores out of the ground, processing them, and do business as usual. But currently, there's not all the high-grade ore accessible anymore. The mining companies currently are also working on what needs to be done to get, let me say, lower graded ores processed on a, let me say, similar cheap way, maybe a little bit less cheap way for the future. So all of these things are currently is work in progress. The other thing, of course, is currently there are heavy investments and heavy investigations and even forced right now with cycling of materials. Because currently and in the past, it was all their batteries when they are at end of life, recycling has never been in focus. European Union currently is in discussion and started the discussion that it will get mandatory to produce batteries in such a way that recycling of the materials will be possible in the future. Mm-hmm. And this, of course, will have another impact on it. Availability. Yes, currently it's tight. Majority of solutions aren't there yet, but since already a couple of years, the institutions, the companies, and so on are working on solutions, and it's even right now forced on that.
Right. On the recycling, we have another question out there, which I'd like to give to our two US panelists. What are the recycling capabilities of various batteries? And is there regulation about this already in the US? Well, one of you, Luc or Joseph, would you like to take this question?
You know, molten salt is interesting because the salt itself, typically called like a thermal salt, it is non-toxic. It has a lifespan of 20 to 30 years, if more, if it's kept within the temperature parameters. So recycling is not so much an issue for molten salt applications.
I'll chime in a little on lithium-ion battery side. This is not my core expertise, but I'll share a little bit about what I know since I'm in the industry. It is a hot topic. I'm not aware of any specific US regulations, but I'm also not policy focused. I'm sure there are different initiatives and things people are working on in that regard. Lithium-ion batteries are different layers of metals. So, in the end, as they age, you get different dendrites that can form. The material itself propagates into other layers. When the battery is no longer capable of holding so much energy, it's because these materials are kind of getting back together again. And you can kind of think of it as if these metals are becoming ore again, and so it's a big chunk of metal. It's very valuable. We will figure out a way to recycle these things because there's just so much value there. So, I really want to encourage people that it's really a matter of it's a little bit of chicken egg, but there's a lot of opportunity. People are entrepreneurial. the recyclers of the world will figure out ways to make sure that we can recapture all of this valuable material that's out there once there's enough of it. You need economies of scale to build these big recycling facilities that are capable of this. We don't have enough big utility scale batteries that are reaching end of life today yet. But once we get there, there will be more and more of this for sure.
All right. Now let's look into the future. So we have the urgent need to scale up energy storage, but we do have the raw material issues. So where will the market be in, let's say, 5 years' time? And essentially, can batteries stand on their own feet, or do they need supportive regulations or support schemes of any sorts? Torsten, what is your view on this?
A little bit of yes and no, because some of the topics, there are frequent business cases out when you to utilize the batteries to really make money with it. It could be arbitrage topics. It could also be the topics with stability, balancing, decarbonizing, but also something like a risk prevention for the industrials. So there are many revenue streams out, how they could live in the future, and the business cases turn out to be positive quite fast. But of course, always the regulators will play an important role. Just to give you, for example, one example, a couple of years we have had main discussions for batteries integrated in grid environments. If you just swallow excess energy from the grid, you stabilize the grid, and this would be in responsibility for the grid, for the TSOs, for the grid operators. If the swallowed energy would be pushed into the grid, this would fall from the regulation point of view under the roof of generators, power plant, IPPs. And both have been separated by law the last couple of years. And without a strong push also from regulation solving these kind of topics, who is allowed to operate batteries or other storage systems with real electrification, without these kinds of discussions, it will really become a tough time to make them self-sufficient. Mm-hmm. I do see the future. Yes, they will be capable, but the baseline needs to be set from the regulators.
Okay. So
if I can, yeah. I'm sorry, Anya. Torsten, that was great explanation. I think adding to that, you know, if you look at, say, the trajectory of wind and solar, or even lithium-ion batteries, I mean, I've been in this business long enough. 20 years ago, you talk to utility planners and you mention wind or solar, and I go, oh, yeah. But there's, but there are policy positions put into play, and the policy also allows for things like investment tax credits, production tax credits, to just try to incentivize the industry to provide what they call missing money, right? If it just doesn't make money, give them some money to make it happen. And it worked great. I mean, over 10 or 20 years, we had huge deployments of wind and solar growing every year. They enjoy learning curves, economies of scale. The prices are coming down. So now they're at the point where in some places, they don't need any subsidies of any kind. They're self-sufficient. And similarly with lithium-ion batteries, I know 10 years ago, if you talk to a utility planner and you mention batteries, they go, oh, like, this doesn't make any sense. But again, policy has a huge play here. I mean, in many of the states that have high renewable targets, they have mandated battery deployments. You know, utilities must secure this much, you know, battery storage technology. And now I think longer duration energy storage systems, compressed air, liquid air, gravity, I mean, basically anything 8 hours plus that's not pumped hydro, which we have gigawatts installed already, these technologies are going to need a policy push from the government, state and federal governments. And they're also going to need some help to get them off the ground, because they, you know, when you put them in a least cost dispatch system where you still have $3 gas producing energy into the system, it doesn't make a lot of sense. But when you look at where we need to be, according to our political targets of 100% clean energy, then they're a necessary part of the system, and we have to make sure that that can happen. So policy support is critical.
Joe, you said in some places they're already self-sufficient. In which places? Please explain.
Well, Texas, Texas is an interesting state. They don't have any renewable mandates. There's no clean energy target. They just let the free market work. And anybody and anybody who wants to come in can do whatever they want. And if you fall flat on your face, that's your problem. Wind has done unbelievably well in Texas. I mean, high capacity factors for wind. And there's a number, I can't name names, but I've seen multiple articles where people have said they don't need subsidies in Texas anymore. Wind can hold its own.
Good, interesting. Luke, is it the same in California, or is that just Texas where storage can stand on its own feet?
Yeah, California is the other side of that equation. So if Texas is the free market king of the world, California is the regulated king of the world. There's not enough rules in Texas, and there's too many rules in California. The reason we're seeing all the growth in California is because of subsidies behind solar that have created the duck curve that the gas plants, that the combined cycle gas plants can't ramp fast enough to cover. So you need storage because of the solar growth. So it's a bit of a different story, but the policy has definitely played a role in California.
In California, recently, they issued a 1,000 megawatt procurement of long duration energy storage, with more coming. So that's an example of a state saying, we have a clear target of 100% clean energy, and they're going to map out the way to get there. And they will put the policy support and the whatever subsidies are needed to make it work. But, this is interesting because I'm a free market type of guy, and whenever I hear subsidies, my eyes wince. I'm like, but you need this to get these technologies moving and off the ground. I mean, the first projects are always the most expensive. You learn from them. The market learns from them. The manufacturers learn from them. Each subsequent project will be lower and lower cost, higher efficiency. But the ball has to start somewhere. And we can't wait until 2047 if you have a target of 100% clean energy in 2050 to start thinking about how do we deploy all of this.
Right.
If I could say one thing, because we're talking about California and Texas, there's two other places in the world that are very similar. There's Australia and there's the UK. These four places in the world are all similar in size from a population perspective, and they all have very similar renewable energy penetrations today. And that's why we're seeing this significant activity in energy storage there, because these grids are big. They need big storage because they've deployed big renewables, because those renewables were the cheapest path forward. And so they sort of created some challenges for themselves that were inevitable. And this is where we're actively solving these challenges as an industry in these four locations as the main hotspots of the world today for battery deployments.
How's the situation in Asia? I mean, it's a very dynamic market. Where are the best places and the most cost economic places to invest into energy storage? Luke, do you want to take this, or Holger?
Maybe Holger can go. I've talked about it.
Yeah, please, Holger, go ahead.
So short before we go to Asia, I think what's great is, to be honest, which kind of success we had and we have already with storage. You mentioned all the places. US, we are not talking about megawatts, we are talking about gigawatts and gigawatts hours, and we are talking about tens of gigawatts, to be honest. And this is not just a tiny small market. You mentioned UK, 1 gigawatt plus. Italy is coming with a capacity market. We also have in Germany already functioning battery market. Also, this is all working. Australia, grid stability. So you're really bringing this child from the kindergarten to school to university. This is really what I think we have this success, and this continues now in Asia. You see different countries. If it will be India or China or Philippines or Taiwan, so there's more or less no country which you can name which is not interested in storage. Right. So this is really just to flip when the start will come. And a little bit about the revenue streams and the market, So we're talking about these capacity fees, or together with renewables or whatever. Everything is applicable in principle to the market, My wish would be with the regulators in the market to be a little bit more pragmatic from time to time, to be honest, and to also have really lessons learned with other markets. Yeah, it would be a great step forward if regulator A would talk to regulator B and C and see the beautiness of energy or capacity or hybrid or whatever markets. I think this would be a great benefit. So listening to the California and Texas, we in Europe, UK, Italy, and continental Europe markets, so a little bit more exchange and a little bit more pragmatism would be a great step forward.
That's a great point, Holger.
And I think there's just one additional point which I would like to add here, because it is quite easy to see when and where the markets will come up. You only need to have a look, when do the renewables exceed, or renewables installation exceed the regional demand. Because as soon as per installed capacity, per installed megawatt, this exceeds, you have excess energy which can be used for storage, and you have two choices. The one is to store it and use it. The other one is to switch off wind and solar power or the renewable generation in these cases. The last currently is not the choice, so then directly you can see where and when storage will come up. Just demanded by the market.
And one last wish, maybe if I can add this, Anja, from this regulatory point of view. We are talking about generation and consumption. And also a kind of wish, yeah, is if you make storage as a separate pillar of the energy system, I think this would be a great help, yeah. That a kind of a definition you have, check mark, it's not a power plant, it's not something else. It's a storage device with a defined amount of megawatts and megawatt hours or gigawatts and gigawatt hours. And for clarity in markets, regulation and revenue streams, I think this would be often a great help in a lot of laws and regulation.
Yeah.
I think that would help too in terms of what you were saying earlier, Holger, about the policy and the regulator types. I mean, it's been my experience. I've sort of navigated between, you know, the industry, utilities, and also policy side, but it's been my experience that the policy folks have grand visions and they have high ideals, but they don't understand power systems at all. And I think having some actual utility planners, grid operators, talking with them to try to formalize a pragmatic roadmap forward would be better for everyone.
Yeah, I couldn't agree more.
Okay, so I understand we have some wishes towards the regulators to see storage as a standalone important device going forward, and we have plenty of technology to offer to integrate the system and to accommodate renewables and make the system more stable. So I would thank you all for your technical and also economic insight. It's been a pleasure to be with you, and I hope we will discuss a related topic in the very near future. Thank you very much for your time.
Yes.
Thank you.
Thank you, everybody.
Bye-bye.
Thank you.
Thank you.
Bye.
Bye-bye.
Bye.
Bye.